Thank you for inviting me this morning to talk about the very remarkable growth that we've seen in the disk drive industry. So first of all, let me show you basically the very simple way that data is recorded onto a magnetic recording medium here. We have some sort of head structure which is made of a soft magnetic material around which a wire is wrapped, or a coil, and you put current through the coil and it produces a flux, and because this is a soft magnetic material that has high permeability, it causes the flux to go around this ring here. Now they cut a little gap into the ring of the soft magnetic material, and because of that you'll get some flux fringing out of below this gap. You pass your media along in front of that head, and because you have magnetic field here, it will tend to magnetize the media either one direction or other depending on the direction of the current. In this particular illustration, the media is moving in this direction here, and you can see that I've recorded several magnetized bits of varying directions. Now, of course, once you've written the data onto the media, you would like to read it back. It doesn't do you any good if you just write it and can't read it back. So here we have the same media, and it's coming along in this direction again, and here you can see magnetized bits. And in this case, I've indicated that there's magnetic fields fringing out of this media by these red lines, and it comes to another recording head here. In this case, I've illustrated an inductive recording head. It's basically exactly the same as the head that was used for writing, and as this comes along, the flux is directed by the soft magnetic material through this coil, and it senses the change of flux in this coil and produces a signal that then can be read into your system, and you can recover your data back. This slide here just illustrates the hysteresis properties of the recording medium. The head actually has hysteresis properties as well, although it's a soft material. But for any storage system, you have to have some sort of hysteresis properties, or else you can't have any storage to take place. This illustrates some important features for the hysteresis properties of the medium, one being that there's a certain moment thickness product that you achieve when you have zero field applied. And there's also a so-called coercivity, and this coercivity is sort of the field that you need to go to in order to switch the magnetization from one direction to the other, so that way I can get either my magnetization in this direction or in that direction there. This actually happens to be media for current products also that's shipping right now into most computer disk drives. Now, another important physical property that you need to understand about magnetic recording, though, is that when I go and I magnetize my media in this direction and then I reverse the magnetization and magnetize it in the other direction, is that ideally we'd like that to be a perfect transition so that we go from one magnetization directly to another and there's actually no transition. But the reality is that you can never achieve that. And so there's actually a transition region here that that sort of limits the maximum amount of data that I can stuff into this track here. And that's governed basically by what the magnetization and thickness product of this media is, and then there's a coercivity that's resisting the magnetization, because anytime I magnetize a material, the magnetization itself produces its own magnetic field that's trying to demagnetize itself when it's there. And therefore, I have to put the coercivity high enough in this media such that I can resist that demagnetizing field and the media remains stable. What I really want to tell you is there is a certain transition width that we get whenever we magnetize two things together like this. You can actually think about this: if I take two bar magnets and try to stick them together, they don't want to remain that way. They want to flip apart. That's sort of the part of the effect that you're seeing there. Another thing I should tell you about the recording medium is that the current recording medium that we use is a thin film material that's sputtered onto a substrate, and it's made up of grains of material that we must record onto. Each of these grains are individual magnets, and they have certain magnetic directions. And because of this granularity of the material, it has an effect on the signal-to-noise properties that I can achieve in the media. So it comes down to, when I want to make a recording media, I have to work very hard to try to engineer and design the medium to get these grains of a certain size and to get certain properties of the grain. You can see already this is actually a pretty old medium here, and here you can see the scale is 10 nanometers. You can see that these grains are already in this 1 to 100 nanometer range that the previous speaker talked about for nanotechnology. And this media is probably about 6 years old now. I want to show you a little schematic of the problem with it because we have granular media. When I want to write a transition, let's say that I had switched my head field from this direction to the other direction at this point here. Ideally, I'd like to have the boundary between the magnetization separated at this line. However, because there is granularity to the medium, I actually find that my transition takes on a shape that looks something like this. And so there's an uncertainty in the position of where the transition is, and that produces the noise in the system. And therefore, that will limit my signal to noise ratio. So ideally, what I want to do is I want to decrease these grains to be as small as possible to get the best SNR. The other thing I want to do is I want to control the dispersion of the grain sizes here so that they're as uniform as possible, because you can also see that different sizes would also have an effect on how well I can define this transition. Now, getting away from the recording physics a little bit, let's talk about what the title of this talk really is, the rapid growth of the areal density in disk drives. And I think the first speaker already showed part of this curve here. I'm actually going to show you the whole historic curve of what has happened in the disk drive industry starting out in 1957 when IBM introduced the first disk drive, the IBM Ramek, and went from there up along this curve. You can see that this is like a 1, 2, 3, 4, 5, 6, 7, 7.5 order of magnitude increase in the areal density from the time this was introduced in 1957 until this year. The other interesting thing is you can see that there's several different regions on this curve where the trend in terms of areal density increase has changed. You know, there's the initial curve where it was kind of taking off rather quickly. People were learning things rather quickly. And then for quite a long period of time, from the mid-1960s up until about 1990, the growth of the areal density went at about a 25% compound annual growth rate. And then we get to around 1991, 1992, and then what happened was that magnetoresistive heads and then later giant magnetoresistive heads were introduced, and we see the compound annual growth rate increase rather dramatically from 25% to 60% at first, and then when we get to about mid-1995, 1996, GMR heads come on the scene and we're going at 100% compound growth rate per year. What this means is that every year we're doubling the areal density of storage in a disk drive. Now, I think this is pretty remarkable when you think about there's this Moore's law for integrated circuits. Moore had said, I think, that he expected that the number of transistors in an integrated circuit would double every 18 months. That turned out to be a compound annual growth rate of about 60% per year. You can see that for a long time, the disk drive industry was kind of lagging that up until the early 1990s. Then we caught up to that growth rate, and now we've exceeded it and are really going full bore ahead. Since this is a precision engineering symposium, and I think we're all worried talking about here, you know, sizes when we get down to between the 1 and 100 nanometer range, it's very interesting to look at what the actual bit sizes are on a recording media over time. And in this case, I'm going to go from 1990, when we see this change from the 25 to 60% compound annual growth rate up until next year, where we expect to see 100 gigabit per square inches introduced in drive products. You can see here at 1990, we still have the track pitch is about 9 nanometers, which is relatively large. It seems gigantic by today's scales. But the spacing between bits was already down to 0.7 microns or 700 nanometers, still not in this nano technology range. But you can see that by 1996, the spacing between bits is down to 150 nanometers, and we're quickly approaching this nanotechnology range. And in 2000, we're below it and rapidly going even further into it. You can see that the track pitch hasn't quite got into that range yet. However, next year, in 2003, when 100 gigabit per square inch type of products will probably be shipped, you can see that the track pitch will be at 160 microns. You should also remember that when I say track pitch, that's the spacing from track to track. The reality is that the write heads have to be smaller than that. They're usually about 2/3 of that dimension, and then the readers are even smaller than that by maybe another 2/3 or so. So you can see that from processing the head structures, they definitely are in that nanotechnology range or getting to that already. Of course, I told you I was going to talk a lot about media, so here we go with some of my media slides. One of the things I wanted to show you is what's happening to coercivity in the magnetization thickness product versus areal density, because this is actually having a major impact on where we're going to be able to go in the future. You can see here I have areal density plotted on a log scale, and also up here the year of introduction of that product. You can see the red dots here show the coercivity. You can see that back in the 1990s, early 1990s, we were down in the 2,000 Ørsted range. And as of this year, we're shipping 30 gigabit per square inch product, which is around 4,000 Ørsteds or so, and we're rapidly continuing to go up. Now, this is becoming a very big problem because, unfortunately, head materials there's a maximum saturation magnetization that head materials can go to that anyone's found so far, which is about 24,000 Gauss. With the 24,000 Gauss material, people have only been able to demonstrate writing coercivities up to about 6,000 or 7,000 Ørsteds. So you can see that if we keep going at this trend in the next few years, we're going to rapidly run into a problem of being able to write. And probably practical realities is I doubt if it's going to be easy to write much above 5,500 or 6,000 Ørsteds in a real product if we continue to go along the same sort of technology that we're using today. The other issue that you can see is that the magnetization thickness product is dropping, and it's dropped rather significantly from 1990. We're down now into this around 0.3 to 0.4 millimu per centimeter squared region. And the reason that it's dropping, I should mention, is because as you want to go to higher linear density, as you drop the MRT, the demagnetization fields go down. That allows you to make that transition much sharper, and therefore I can get more bits packed along the track. So that's why it's being forced to go down so rapidly. Of course, we continue to increase the coercivity to keep it from demagnetizing. I'll talk about it in a moment, though. The problem is that as we do this, these grains, you have to remember I showed a plan view of the grains, and they're these nice sort of cylinder-type objects you might think of. They're not exactly that. But you have to remember they have the thickness, too, and the thickness goes all the way through the medium. There are not multiple grains in that media. So as this MRT goes down, you can see that the grain volume is getting smaller. I'll talk a little bit more in a little bit about as that happens, we run into superparamagnetic limits rather quickly. Of course, another thing that we have to do is that in these disk drives, the head is built into a slider sort of form that flies over the disk, quote unquote. And flying is maybe not really very accurate these days. You can see in the mid-1990s, we were like at 70 nanometers. We're definitely in this nanotechnology range. If you talk about flying height, these heads are flying very fast across the surface at very low spacings. You can see that we're down here about 30 nanometers right now, so we're about at 15 nanometer fly heights, and we're headed down to below 10 nanometer fly heights in the not too distant future. And it's really questionable what we're going to do as we get out here. We may be reaching limits of physically where we can actually put these heads in relation to the disk. And in this region here, most likely we are no longer flying, but rubbing along the disk. And so that, to me, sounds very scary because you usually get catastrophic problems when you have these interactions of that happening. But this is important because there's a spacing loss that occurs because of the flying and limits what linear density you can go to, and that's why we have to shrink that. You can see that one of the other things that we've had to do as we've dropped the flying height is the smoothness of the disk must be continuously improved with increasing areal density. The RAs of media of disks right now down in this region are something like 3 to 4 angstroms. And we need to go down to about 1 to 2 angstroms to get out into this region here. I showed a little bit earlier a TM plan view of some media grain sizes. And if you want to talk about nanotechnology, people who make media, I think, would contend that we've been doing nanotechnology for years because we've been trying to control our physical grain sizes in ranges where you can see in about mid-1990 we were in the 20 to 22 nanometer range. It's much lower than this 100 nanometer limit that was talked about earlier. We're today down in a range that we're about 8 nanometers, and we're headed to a range where we think we have to get down to in the range of 4 nanometers in the next 5 to 8 years. Here's a plan view TM of a 30 gigabit per square inch medium, which is currently what products are shipping today. It's sort of the highest areal density being shipped today. I should point out most of these grains are only 30 atoms across. The grain size here is about a little bit less than 8 nanometers. I think in this case we thought it was about 7.5 nanometers. That's always a matter of debate how you measure them too, and we could discuss that for a long time as well. The other thing you can see that's very important is that there's little grain boundaries around these grains that isolate the grains and keep them from contacting each other. Otherwise, they're not magnetically isolated anymore. And those grain boundaries are about 2 nanometers in thickness. And ideally, we want to control these to be as uniform as possible and control the dispersions to be as small as possible, too. Another thing to show is a cross-sectional view of the same sort of medium, because that also involves us putting down layers that are in the nanometer sort of ranges. We start out with typically it may be aluminum substrate that is coated with a nickel phosphorus layer on which we start to sputter a seed layer. In this particular case, it is about 7 nanometers in thickness. We then put an underlayer of about 5 nanometers, and we have to grow then a nucleation layer of about 3 nanometers. On top of that, then we put our magnetic layer, which is about 14 nanometers. And we have to control these layers very precisely, because if we don't control them well, it affects the signal-to-noise ratio properties and other properties of these disks rather severely. So this takes a lot of effort. And remember that we have to manufacture these by the millions per month. And going forward, this actually shows a TM of a 60 gigabit per square inch product. This is the sort of product that will be coming out in drives in the second half of this year. And what I didn't tell you, and maybe I'm not sure how well it's going to show up here, this actually is a 100 nanometer distance here, line here. It doesn't show up very well on this picture. What I didn't tell you is one of the things that's also done is that there's actually texturing that is put on these substrates that helps to guide the grain growth. And actually, if you look closely, and it may be hard to see with this display, but these little texture lines are about 18 nanometers across, and there's about 2 grains in each of these texture lines. And the reason these texture lines are put here is that it causes a preferential alignment of these grains, and it causes the magnetic properties along this direction to be favorable for recording, and along this direction not to be favorable for recording. That has an impact on signal-to-noise ratio. But it's becoming very critical these days that we control very precisely the size of these lines and the uniformity of these lines. And I said we're at 18 nanometers today. We'd like to half that within the next year or two, and hopefully get maybe 1 grain in each, across each line instead. And this is going to be a very big challenge, and it's actually an area that has not been explored real well yet, and will cause a lot of work to be done in terms of how we do this texturing of the substrates. Now, the first speaker had mentioned this superparamagnetic limit for magnetic recording. This slide actually discusses that problem in more detail. The problem is that if I have a grain, let's say, that's magnetized in a certain direction, there's a certain energy barrier that prevents that grain from changing its magnetization to the opposite direction. Now, that energy barrier unfortunately is being excited because there's thermal fluctuations going around in the environment, and there's some probability that that this grain will flip spontaneously to the other direction here. The energy barrier here actually for preventing that reversal of magnetization is represented here by this equation, where basically I have an anisotropy to the material, and then there's this grain volume, and that grain volume is a very important thing to think about, because basically it's the diameter of the grain and the thickness of the grain. And I told you already that the MRTs are coming down, that's making the thickness come down. Secondly, because I need to get signal-to-noise ratio, and you saw my chart, the diameters are shrinking, and therefore I'm pushing this volume smaller and smaller and smaller. And so that's rapidly pushing me into a problem where this energy barrier is dropping and dropping. And one of the things that I need to tell you is that in order to get 10 years of storage, this product of KUV needs to be about equal or greater than about 40 times KT, where K is Boltzmann's constant and T is the absolute temperature. Now, what can we do to reverse this problem? Well, one of the things that you can easily do is you can make the anisotropy go higher. The problem is that as anisotropy goes up, the coercivity goes up, and now we have a hard time recording the magnetized bits with the head. And we're running into a limit where the maximum saturation magnetization materials I mentioned earlier for a head material can go no higher. No one knows any material that has higher saturation magnetization than that. And therefore, this means that we need to think about different methods for how we're going to do our recording that will try to make sure that KUV is higher than this quantity here. The other thing I should mention is you saw the TMs of the grains of the medium. There's actually a distribution, which is a log normal distribution of these grains. And so that's another issue that we have, is because we don't have all the grains perfectly the same size. One of the problems you'll have is you'll have small grains, and they'll tend, because they're smaller, their volume is smaller, they'll tend to switch their magnetization spontaneously more rapidly than, say, these large grains out here. The problem with the large grains out here, of course, is they have poor SNR, and they will tend to make the SNR worse than we would. So ideally, we'd like this nice and sharp, almost a delta function if we could, and control the number of small grains we have here. And we're doing that all the time, and actually have made a lot of progress in controlling this. We, of course, don't get a delta function, but we are able to narrow this down. And that is actually, starting about 3 or 4 years ago, people really started to have problems in products where thermal stability was an issue, and you would see this decay that was unacceptable for this 10-year lifespan that's required. And so we've worked very hard, and we can control this to some extent, but it's not enough. So we have to look at other solutions. One of the solutions that has gotten some press recently and is being used in some drives is a so-called synthetic antiferromagnetic media, or SAF media. And this shows a cross-sectional TEM of that structure, and also a schematic discussing what the structure really is. It's very much similar to the structure I showed previously, with the one exception that instead of having just one magnetic layer here, you have a bottom magnetic layer here. You separate by a very thin layer of ruthenium, and then you put a magnetic layer on top. This ruthenium layer here has to be on the order of 7 to 8 nanometers, plus or minus about 1.5 to 2 nanometers. And what happens is that once you put this here, you get a synthetic antiferromagnetic effect, such that if I magnetize this top layer in this direction here, it forces the bottom magnetic layer to be magnetized in the opposite direction. And what happens then is you get cancellation of some of the flux between these two layers, and effectively it lowers our MRT, which we need to do in order to get high linear density and high resolution. But and normally when we would do that, we would lose grain volume. But actually, what happens is the grains between this layer and that layer are actually epitaxially grown, and they're actually exchange coupled through here. So the grain volume is actually the combination of this volume plus that volume together. And so we get more volume but lower MRT, and therefore we can maintain thermal stability to some extent longer. Here's a hysteresis loop for that type of medium, showing the switching properties of that medium. If I take and I saturate it all in this direction here, and now I lower the applied field, I get to the point that the bottom layer now flips in the opposite direction of the top layer because of the antiferromagnetic coupling between the two layers, and therefore that's the state I end up leaving it in after I record it and take the head away. And as I said earlier, my MRT effectively is the difference between the MRT of the top and the bottom layers. That gives me my good resolution. But my switching volume is actually the combination of the two layers. So I get a big volume again to maintain thermal stability. But that will only probably take us a little bit farther where we need to go. And I'll show in a little bit how far I think it will really go with that. So beyond synthetic antiferromagnetic structures, what else is there? Well, one of the things that's getting a lot of work these days is perpendicular magnetic recording. I didn't really make a point of it, but if you notice from my first slide showing how we record, we always try to magnetize our bits into plane, either this direction or that direction there. And as you know, if you take two bar magnets, they don't really want to be in that sort of state opposing each other. They're trying to always demagnetize themselves. But you also notice that if you just kind of let two bar magnets just kind of go by themselves, they tend to flip and they align this way, and they really like that structure very well. So one idea that's been around actually since the beginning of the disk drive industry really is, well, why didn't we just magnetize bits up and down? There's a lot of issues involved with that. Part of it is how you really get the field into that structure well to magnetize well. And there's some many other issues as well, and part of the reason it hasn't been introduced yet. But this is sort of the structure that people are really investigating today. It kind of solves a recording issue, and it solves another issue too. What we do is we have a recording media here in which the magnetic orientation is in the perpendicular direction. We have a head structure that's modified, and we have this very thin pole here where flux gets concentrated. And then what we do on the bottom of the recording medium, we put another soft magnetic material, and that acts as a flux guide to guide the flux directly through the medium, and then it goes through the soft material here and then back up through the head here. Unlike before with longitudinal media, where we have field fringing out of this gap, and it hopefully has to get to the medium, in this case, we actually are putting the medium effectively inside the gap of the head. So we can get much more field out of this sort of recording structure than for the longitudinal recording type head. And people have estimated maybe you can get as much as twice the amount of recording field. So instead of maybe going to 5,000 or 6,000 Ørsted media, there's a hope that we'll get to 10,000 or 12,000 Ørsted media with this type of structure in the near future. That will be good because that means we can continue to shrink that size of the grains, and we can make the anisotropy go up and maintain thermal stability. But what happens beyond perpendicular media? Is there other solutions here? And I hope this shows up okay. One of the things that many researchers are currently working on is a thing called pattern medium, where, and I guess this is sort of like the first speaker was talking about digital versus analog. In some ways, we're using analog right now to allow these grains to kind of grow in a certain way in our medium. In the future, what some people are thinking was, why don't we do digital and we'll kind of hack away at the medium and pattern each recording bit to our liking. Instead of allowing the grains to form where the transitions are in the heads, we'll actually pattern where we want bits to be. Okay, so I'd like to show you my predictions of what I think will be happening for the rest of the decade for the disk drive industry in terms of areal density growth, assuming that we go at this 100% compound annual growth rate per year. And of course, that's a question whether we'll maintain that or not. You can see right now we're using conventional longitudinal media, and we're down here in the 100 gigabit per square inch and below sort of region. Some people have gone now to synthetic antiferromagnetic longitudinal media, and we predict that, and almost anyone in the industry will predict that we think that we will not get much higher than about 200 to 300 gigabits per square inch. Beyond that, we have to go to something else. What most people think that something else will be the perpendicular recording medium. But even as we go to perpendicular recording medium, there's a lot of belief that that may only get us up to about the 700 to 800 gigabit per square inch sort of range. Beyond that, it's almost anybody's guess, although I think a lot of people will think that bit patterned media will take over as long as we can figure out how to pattern these sort of media. Like I said, there's a lot of efforts happening on that, but a lot of questions too whether we can make that go. And as I wanted to say that for this Precision Engineering Symposium, I think you would be very interested in seeing the sort of physical feature sizes that we'll need to go to continue along this curve. So if we look at the linear bit density and where we're at, of course the linear bit density in thousands of bits per inch is continuing to increase. The actual minimum bit spacing is coming down. This year at 2002, we're at a bit spacing of about 45 nanometers. But by 2008, we'll be down in the 10 to 20 nanometer range. All these are sort of in that nanotechnology sort of range that we've been discussing today. From a track density sort of forecast, the track densities in thousands of tracks per inch continues to go up. If we look at the actual track pitch that's associated with those, it's going down rather rapidly. In 2002 of this year, we're maybe at about 300 nanometer track pitch, but maybe about 2005 to 2006, we'll go below 100 nanometer track pitch into that nanotechnology sort of range, and we'll continue to slide down further into that range and be maybe at about 50 nanometer track pitch by the year 2008. So in conclusion, what I would like to say is that there's a lot of challenges that lay ahead for us in terms of how we're going to achieve these. There's still many uncertainties, but there's a lot of engineering and science that needs to be done in order to allow us to progress up this areal density curve. And I'm hoping people out there will have many ideas that will help us. Thank you very much.